did that with Muriel this was not available, so we proved that by just proving the isomorphism by induction. So voilà.
Bon, on continue là.
Okay.
C'est trop, hein.
So let me start again. So I have finished. I was speaking about this group of 3 index series, and what I want to do now is to explain a little bit why people in numerical analysis have been using these things, and also to talk about some examples of interesting 3 index series, which are like the logarithm and the exponential. But before that, I have still a few things to say on this group there, or monoid, or even on the monoid. So we have there's an interesting projection, morphism of group, which goes to formal power series for composition. And this just amounts to, if we have here a sum over all trees, it maps it to the sum of all, well, we just keep what I call linear trees, which means just the trees like that.
So map all other trees to 0?
Yes.
Or
okay. In some sense, yeah, you see we have a polynomial series. It has just integer indices. What it means is that the coefficient an here it's the coefficient of, so let's call it at times t. So it's just a of with n vertices. So we just forget almost all of the coefficients, but the coefficients of the linear trees. And this is so why is this a morphism of group? Because this guy is just the same thing for Assos. And we are using the projection map of operads, which does exactly that, which maps to 0 everything which is not a linear tree, and is the identity one, which maps a linear tree to just to the usual basis of the associative operad. So we see that this group of 3 index series, well, we knew already that it looked like a group of composition, so okay. But there's something which is a bit more funny, which is to keep only corollars and map it to the group of formal series of, let's call it another name, so let's call it X for the product. So here, it's the same thing. I make a sum of n greater than 0 of a n, or let's call it here, bn x to the n, and this bn well, let's put it like that. So this bn is the a of corolla with n leads. And well, okay, so we see that it's a bit surprising, because this group, we think about it as a group for composition, and it has a morphism to a group for product. This can be seen also from this functorial's point of view, because we have some kind of pretty modulo non-corolla. Well, if you the non-corollas form an ideal in the pretty operad, so we can take the quotient and we use as a quotient operad, which is a bit ugly, which is not very of any overuse in some sense. But this gives this map from 3-index series to usual power series for product. Okay, so maybe I will use that later at some point. It's I like this kind of mixture between product and composition. That's a bit. Okay, now let me try to explain why this has anything to do with vector fields and numerical analysis and things like that. So the point is, in fact, this theory of Butcher series, so the results of Butcher's, they go back to the 60s, and since then they have been used a lot. So these are the results on Runge-Kutta methods and things like that. But for me, in some sense, the story goes back much further, because the first mathematical article in which there were drawing of trees, just like a bit like the drawings I've made today, it is an article by Cayley, and it was in the 50s, but in the 50s of the century before. And we can, well, this article is available in Cayley's complete works, and we can see then drawings of trees. And so let me present what Cayley did in a modernized way, in modernized form. So we place ourselves in RD, and we look, well, we choose coordinates x1 up to xd. And we look at vector fields. So I will do not bother about, well, let's say polynomial vector fields if you want. Or, yeah. So a vector field, a typical vector field can be written as a sum from 1 to n of some coefficient. Okay, it's not a good name. Vi d dxi. Okay, it's we just write it in coordinates. So there's a function. Let's assume that it's a polynomial, and this is a differential operator of order.
N equals d, no?
Oh, sure. Yes, thanks. So it's a differential operator of order less than 1. Now, if we take two of them, then we can define the composition as differential operators. And this has the following expression. So it's the double sum over ij of vi d vj dxi d dxi plus the sum of ij of vi double j d over dxi d over dxj. Okay, this is just the composition of differential operators. Of course, we know that if we take the bracket, the commutator of this thing, it's a vector field, and it's the usual Lie bracket of vector fields. But now we decide, in some kind of arbitrary way, that we are just going to keep this part. This is a differential operator of order 2. We keep the part which is a differential operator of order 1. And we denote that by, okay, so It's V. It's a well, okay. The pretty algebras before they were right-sided, and now they will be left-sided. I can.
Where's the J? Sorry.
Where's the J? So there's a J there. The J is the index of W. Yeah. So that's. Okay, so of course we can say this in more fancy geometric terms. It's the flat connection on RD and things like that. I'm just sticking to concrete language. And okay, so the first claim is that this is a pretty product. If you want the pretty product to be the same as before, maybe we should write this as. So I've written them that way. It should be. Well, if you want to have the same axiom as exactly the axiom I have given before, we have to revert the two, but it's not that important. So this you can check by yourself if you want. There's this famous, this four-term identity. And one can check that with this formula we have the equality of these four terms. Okay. Now we have these three Prelli algebra on a space of dimension 1, and we have its universal property, which is that given any Prelli algebra and any element in this Prelli algebra, we can find a map. So here, given any vector field, let's call this vect of RD. We have a map from. We have a morphism of Prelli algebras, which maps the generator to V. And so this gives.
So this circle is a graph with a single vertex.
Yes. So it's it's a tree with one vertex. Okay, so this is just the statement of the universal property applied to the Prelli algebra vector fields, and so okay, we choose a vector field, and then what we obtain is that for every tree we have some vector field. So there's there's a name so there's, I think the classical notation is something like ft of v, and these are called the elementary differentials. So given one tree of a vector. Okay, so now everything is in place.
Did you say this is due to Cayley? All this?
Well, this needs the Prelli algebras, and Cayley did not have axioms. What Cayley was doing, he has defined this operation. He has declared that I want to name this operation, and he observed that when you do that, you see formulas can be described by trees. If you look at the image of a tree, by this, so this works more generally. You can take here any set of generators, and if you look at the image of so this corresponds to trees with colors, and if you look at the image of a tree with colors, where each color is mapped to a specific vector field, then you can see the shape of the tree in the formula, in the coefficients for this vector field there. So well, Kelly have seen trees, but he had not the abstract notion of Prelude algebra, so he...
Did he introduce these elementary differentials?
No, the elementary differentials, they are very classical. I'm not sure I can attribute them to a precise person. Maybe Kelly already.
But around that time, around the late 19th century, were it being used?
I don't know where the name first appeared, but implicitly this is in Kelly. Yes. Yeah. So there's nothing much new. Okay, so now what do we do with vector fields when we want to look at the flow of the vector field? So V, a vector field. So we look at the flow equation. So we look at a function from R to Rd such that the value at 0 is some fixed point in Rd, and the derivative and it describes the curves, the curve in Rd, and the tangent vector at each point of the curve is given by the vector field V at this point. So it's the classical flow of a vector field in a fine space. Of course, I'm not going to take any analytic precaution, so of course there are issues of convergence and things like that, and norm, and well, I'm not concerned with that today, and in general, not much. Yeah, I understand it's necessary, but I don't want to.
No, but the machinery which is this RDM gives also insight into it.
Yes, that's true. It's also useful to understand these things. Okay, so we just look at the formal solution of this thing. So of course we know that Z of t, well, at t, well, first Taylor expansion. So it's then it should be v of z0 t plus, and then it goes on a Taylor expansion with respect to t. And so one can compute this Taylor expansion by induction, and we'll see that in fact the next term will be just the Prelude product at z0 t squared over 2. And it goes on. So the general formula, the general solution is that z of t minus z naught is the sum for n greater than 1 of Tn over n factorial. And here we have the iterated Prelude product, sorry. So what does this mean? This is not an associative operation, so we have to specify what bracketing we make when we take the nth product. So it's the right bracketing. So it's V, 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 and so on up to V with n V's. Okay, so just one V, and every one of these guys has to be taken as Z0. In some sense, this is a well-known formula. Maybe people use rather the flat connection to say this formula, but it's nothing, and it's an easy induction that proves this formula. So there's not much mystery there. But what's interesting is that this formula just uses only the Prelude product, and so we can see that, well, it's the image by this map. So we can take the sum here, the sum of t to the n over n factorial, and here we take the this tree iterated n times, and if we take the image, then it will be exactly sum over v iterated n times t to the n over n factorial. So we can define an element in prelee of Q, well, with some extended with t's, with coefficients in formal power series, whose image is exactly the solution, the formal solution of the flow equation. So it's some kind of once we have done that, we can forget about vector fields, and we have something which is like the universal solution of all flow equations.
So what is the tree which is a coefficient of T and T?
It's not a tree. It's a so if you it's the iterated prelee product. So if we look at the first few terms of this formula, we'll have this guy, then this guy's times t. No, I'm mistaken. Oh, sorry. It's this time t plus this time. Yes. T squared over 2 plus. Okay. Then we at every step we have to take the prelee product of this guy and a new vertex which comes and is glued over it. So it's adding a new vertex in every possible way. So here we can add a new vertex either on the top or either on the root vertex.
Is this related to the Kohn-Moscovici?
It's in Kohn-Moscovici it's called the natural growth operator. Yeah, so it's the same thing.
It's the same one?
Yeah.
Oh.
The same formula, and I can well maybe write just the next term. I'm not sure. Somebody. Okay. So the next term there's it's a bit there's starting to be coefficients in the multiplicities in the trees. Okay, so this sum is obtained from this one by looking at all possible ways to add one more vertex and then gathering the trees which are the same shape. So there are 3 possible ways here, 3 there, so there should be a total of 6 trees, but this one appears three times. Okay, so now imagine that you have but you want to approximate the exact solution of then what you want to do is to have something which looks like which has the same Taylor expansion as the formal solution up to some power of t. Then for this you have to look at just the same thing here. You have to look at 3 index series which have the same expansion as this specific one up to some power of t. And this is exactly what they use in the study of Runge-Kutta methods. There's something I don't want to tell about is, I don't want to enter the details how to go from a Runge-Kutta method, which is mostly just a square matrix. There's a recipe to compute a 3-index series. And if the Runge-Kutta method is good up to, if this 3-index series for a Runge-Kutta method coincides with the exact solution up to degree k in t, then it has order t, and the higher k, the better. Well.
And does it go the other way as well? So I mean, if you know sufficiently many terms here, can you find a good Runge-Kutta method?
Yes, it's the set of 3-index series coming from Runge-Kutta method is dense in all 3-index series, but at the price of having larger and larger matrices. So you have to trade the simplicity of the method for the order of the method. So the order is the degree up to which it approximates the exact solution.
No, but if I've computed this series to degree 7,
yeah.
can you give me an algorithm how to construct a Runge-Kuthe method?
No, because the Runge-Kuthe method is a matrix, and then the coefficients of a tree in this associated tree index series are complicated polynomials in the entries of a matrix. So it's not easy to solve. It's finding points in an algebraic variety, which may be arbitrarily complicated. So no, it's not easy to find a Runge-Kuthe method with good properties. And it's people have made a lot of work to find some. Okay, so now I will just get rid of the t, and I will just consider this formal sum with t. So I just put t equals 1. Okay, and I define A, which is the sum of n greater than 1 of bullet 3 and other. So this is an element in the tree, in the group of tree index series. Of course, it's invertible because it starts with a non-zero coefficient in degree 1. And okay, now I want to spend a little time trying to talk about some examples of interesting elements in the group of tree index series. So here's one. This is an interesting element because it came from somewhere else. It came from the study of vector fields, and it gives I have not chosen the coefficients at random. The object came from somewhere else. Now there's something we can do because we are in a group. We can look at the inverse. Wow. This is also something which is used by people in numerical analysis. They are doing something, well, they call that backward error analysis. And what they do is they have a vector field and its flow. And they have approximate method which give an approximate solution to the flow. But now they think, oh, I have a bad method. But if I change the vector field, maybe I can find with my bad method the exact solution. And well, in this kind of, well, I don't want to, I'm not really able to go deeper than that, but they are using the tree index series, which is the inverse of A in the group, and so there's also some motivation. And so, I want to say I should, well, I forgot. I wanted to say something on the coefficients there. You see these numbers there? These numbers are easy because they just count increasing labelings. Well, increasing trees with this shape. So if I want to understand why there's a 3 there, I have to look at all shapes which are labeled, all trees which are labeled by the integers from 1 to n, and which are this shape when I forget the labels. So how can I fill the vertices of that guy in an increasing way, so increasing from bottom to top, by integers from 1 to 4. So of course 1 has to be the root. And then there are 3 choices because I can put here either 2, 3, for 4. And then there's no choice for the remaining parts. So. And so this is the way the coefficients there, they count this thing. They count trees labeled in an increasing way by the integers from 1 to n, and such that the shape is the shape we are looking at.
Truncated.
Yeah, soft. Well, it counts something like the linear extensions of the tree.
But then you divide by automorphisms, or I mean, because why isn't the coefficient of the last term 6?
No, because one has to be precise in the way to state the thing. So we look at trees which are labeled by integers from 1 to 4 and which has this shape. And so they're just 1. There's just one way to put integers from 1 to 4 in this shape.
The shape is not what is
That-
on
Yeah,
the blackboard, it's
Yeah.
the abstraction.
Yeah.
Okay.
Yeah.
No, so if
So
I were
it is
to put
already-
it on the
also
blackboard, I
already
would
disappeared.
mod out by the I had
Yeah,
divide by
but
tomorrow.
no, it's abstract trees. Okay, so but there's another way to it's very convenient, in fact, to introduce this symmetry factor. So I want now to write A in another way. I want to write A as a sum of a t of some coefficient at, but with here the what's called the symmetry factor. So it's the so what's that? It's the cardinality of the group. So we take we label T in some way. So for example, like that, and we look at all permutations. So there's an action of S4 there, and what are the permutations which give the same tree? Here, there's just the identity. If we look there, and we have also an action of S4. So there, what are the permutations which give the same tree? Then it's the symmetry group, which it's the S3 which fixes the label of the root. So it's the S3.
So you divide by the number.
So here
That's why we have all these one notes.
So if I rewrite what I had there using the symmetry factor, it would be this plus 1/2, and then here the symmetry factor is 1, plus then there's the symmetry factor is 1, but I have 1/6. Then I have this guy where the symmetry factor is, so it's a symmetry group with 2 elements, so it's just 2, and the coefficient was 1/6, so there's 1/3 there. Okay, I'm just rewriting the same, well, t equals 1, but small t equals 1. And I can, do that. And so now this coefficient there, where I have separated the symmetry and something which remains, they have, they are volumes of a polytope. And also something else, they are 1/3 factorial. Of t. So I should explain these two things. Let me just do this there. So maybe I start with the 3 factorial. So the 3 factorial, it's a generalization of the usual factorial of a number. And the principle is that if you have a tree, so if you have something like that. So a tree T, which is a root, and then T1, T2 up to Tk. Then the tree factorial is just the number of vertices of T, so it's times the product of the Ti factorial. So it's a recursive definition. And if we look at this guy, so its factorial is 4 times the factorial of that one, so it's 3 times the factorial of that one, so it's 2, 1. So it gives the usual factorial for the linear trees, and when we take a corolla, here it's 4 times the factorial of this one, factorial of this one, factorial of this one, so it's 4 times 1 times 1 times 1. So it's an integer, and so we can check, for instance, for this corolla there, it's 3 times 1 times 1, and we got 1 over 3 there. And okay, well, this is not complicated. This is just very classical things, and we can find that also in papers of Kramer. Now, what about the polytop? Well, we can see a tree as a partial order. So simply by saying that the smallest is at the bottom, and so a partial order increasing from bottom to top. And we can put a variable inside each vertex, and then we can look at the set where all these variables, okay, I'm just doing an example, are between 0 and 1, and the value is increasing. So x smaller than y, x smaller than z, and z smaller than t and v. Okay? And so this is a polytop. This is okay, this lives in R to a power of the size of t, and it's even in 0, 1 to a power of the size of t. Just one concrete example, we can look at this one, because this it's in dimension 3. I can make a drawing. Try to make a drawing at least. So it says that x should be smaller than y and z, and all between 0 and 1. So it should. It's some kind of pyramid with basis. So it's something like that, and then. Well, maybe I'm mixing the x and the y, but it's a pyramid with square basis. And what's the volume of that pyramid? So it's a unit square basis, and we have a formula. So it's volume is 1/3. Okay. It's the same 1/3 as before. So in some sense, these formulas are fun, but it's very classical in some sense.
I'm sorry, can you say again how you build that polytop inside the cube? Can you say it again? I'm sorry.
Well, you have to look at the points where x is smaller than y, x is smaller than z, and everybody is between 0 and 1.
Ah, yes, well, I'm sorry.
So it's the intersection of two, well, you have to convince yourself that this guy looks like that. But it's an exercise of geometry in space. And maybe the y, the z are somewhere not. Well, so these coefficients are not really interesting. What's really interesting are the coefficients of the omega series, which is the inverse of A. And let me just write. Okay, maybe you are starting to get tired, so I will not go. I will not do everything. So let me just start the first. Wow. You know, the theory omega, one can start to compute, so it starts like that. Because this 1/2 becomes this -1/2, it's just the first expansion, and then it gets more and more complicated. And for example, if we look at this one, then the coefficient there is 0. Some coefficient vanish. And if we look at the coefficient of, well, of that guy with 12 leaves, then the coefficient is minus.
Peter.
So it's a Bernoulli number. And so in some sense we can the coefficients of a series omega are complicated rational numbers, and there are something like 3 Bernoulli numbers. Why is it true? Why is it true? Because remember that I have these two morphisms to Power series for product and Power series for composition. What I say is that the image of A on the left-hand side is just e to the x minus 1 over x. And the image of A on the... So this is the product side and this is the composition side. This is the projection on corollaries. And this is the projection on linear trees. So if I take the inverse of A and project it onto corollaries, it's the same as taking the inverse here. As this inverse is the inverse for the product. So it gives x over e to the x minus 1. And it's the generating series it's a formula for Bernoulli numbers.
And at the coefficient of the chain symbol.
Oh, the coefficient of the chains it's the same principle. You look at here, and you invert this function for the composition. So it's a log. It's it's something like minus log 2 signs. So the coefficients are just 1 over n. Okay.
But is this including the symmetry factors or not? You had two different normalizations for A.
Yes, it's with this normalization there. The Bernoulli numbers are once we have put the symmetry factor in the equation. Okay. Well, I have a few more things to say, and let me try to summarize. So we have some other way to compute these coefficients. These coefficients can be obtained by doing something with a polytope. So the statement, maybe I just write the statement and I will not explain everything. So let's write sum of omega t over odds of t. Then omega t is, well, okay, more modulo some details. It's the derivative at -1 of the Erhard polynomial of the polytope associated with T. So there's a recipe to compute. If you want to understand to compute one of those coefficients, then you have to compute to look at the polytope, to compute its Erhard polynomial. So it's something which counts lattice points, so points with coordinates which are just integers or rational with a prescribed denominator. It's a polynomial in one variable, and because the polytope has no interior point, it vanishes at -1, and then we can look at the derivative at -1. Okay, I cannot really explain in 30 seconds what's all this thing, but there's another way to find. And so the Bernoulli numbers, they appear because they have, if you look at pyramids, then the Erhard polynomial of a pyramid is a Bernoulli polynomial. And you more or less, then from the Bernoulli polynomial, you go down to a Bernoulli number. Okay.
And there is an interesting comic paper by Sylvie Péchons or something. She reported it in my paper.
Okay. So my interest in all these things, I'm trying to find interesting examples of tree-index series. So here I have 2 of them, but of course, a priori, I don't know where to search for interesting examples. And it happens that this omega, we can find it in some other way because it comes from some algebraic construction in freely algebras and things like. Okay, so we have another way to find omega, and this other way gives us many other interesting examples. Well, I don't know. Maybe just okay. So omega comes from something. So we have one object there which I call. Which gives omega, which is a sum of Lie idempotents in the descent algebra of the symmetry groups, well, some algebraic thing. But this guy has a Q analog, meaning we can introduce a one-parameter family of analogs of this guy there. And so we obtain a one-parameter family of analogs of omega. And so the coefficients, I call that omega Q, and the coefficients, so they are fractions in Q, and when Q equals 1, we get back omega. And
is there an AQ as well?
Well, sort of, yes. There's a Q3 factorial, but it appears for other reasons. It's not the same. Okay, so then on this side there are other examples which are not Q deformations of that one, but which provides new interesting examples of tree-index series. So okay, I could go on and say more things, but I think we don't.
Can I ask maybe a strange question? Yeah. So this A is somehow a flow, or has to do with a certain flow.
Yes.
Flows have Jacobians. I mean, any homomorphism, any diffeomorphism.
Yeah.
So can you compute the Jacobian of A in a reasonable way in this formalism?
Well, I think I see where you want to go, because there's the Jacobian conjecture.
No.
No, that was not the motivation.
No.
I think it does not fit very well in this setting. People have been trying to use this tree-index formalism to prove the Jacobian conjecture. And so far, it does not really function. It does not lead to anything. And the Jacobian is not easy to express in this language, I'm afraid.
I'll expose my ignorance and tell you that I have no clue what you're talking about.
The Jacobian conjecture?
Yeah.
It's well, it's a conjecture which says that if a polynomial automorphism of an affine space has non-zero Jacobian everywhere, then it has a polynomial inverse.
Okay. No, but
it's an important conjecture which is open for a long time.
I believe you, but I mean,
No,
I don't see why it would be related. But okay.
because it's a conjecture for every dimension, and if we manage to formulate it in terms of tree-index series, we would have one thing to solve for every dimension. The Jacobian conjecture is easy in dimension 1, but it gets harder and harder with every dimension, and so yeah. So, no, I'm sorry, I thought it was a question, but
Do you look at differential equations that are satisfied by Howard series or Dyson-Schwinger equations?
yeah,
Is that
I describe them by equations, and I have global equations for them, which are
there's something like, I don't
they
know.
are more like algebraic equations in some sense. They don't involve any differential. Because there's not really a differential on tree-index series. There's no real way to go from trees on n vertices to trees on n minus 1 vertices. So it's more like algebraic equation.
There's but one in all possible ways.
Yeah, that's one possible. Yeah.
Okay, but there is no natural.
So I can this A and these omegas, they satisfy something which would fit in part of the board, but I would need notations to write this equation. And so essentially it uses the Prelli product and this composition, some ingredients like that.
Since this A looks like an exponential, if you
Yeah.
take the product of two of them, do you have kind of Poincaré?
Okay, the A and the omega are like exponential and like logarithm, and then there's more to that because there's an analog of a Birkhoff.
No, Baker-Campbell.
Baker-Campbell-Hausdorff formula, which uses them as exponential and as logarithm. These two series play this role for a Prelli analog of Baker-Campbell-Hausdorff. That's one thing, but they are not there's another theory which is just the sum of a t over auth t, and this one is also an analog of the exponential, and it's it's the one who, when you take the product of this one by this one, it's this one again. So yeah, so this is rather this one the answer to your question.
Maybe I'll say in a few words why I asked you what it definitely wasn't what you said. So, so there is a very, very similar formalism well, actually hidden in papers on Alexeyev Torossian, etc., and Kashiwar Verne.
Mm-hmm.
And the point is, they want to, or roughly speaking, they want to show that two integrals on a Lie algebra are equal,
Mm-hmm.
and they do it by finding a flow that takes the one integrand to the other integrand,
Mm-hmm.
but then they have to show that this flow is measure preserving, which amounts to saying that the Jacobian is 1,
Mm-hmm.
or, and I'm lying in many places, but this is the rough, but at least you need to have control on the Jacobian. And the way you find this flow is by flying the vector field that generates it.
Mm-hmm.
And it can be expressed as an element in the free Lie algebra. So this has to work for all Lie algebra. So
Mm-hmm.
the formulas for it involve finding elements in the free Lie algebra. In a free Lie algebra, so
Yeah.
you have trees that represent vector fields, and you exponentiate them to get flows, and you get very similar formulas along the way. And at the end, you want to compute a Jacobian, which is actually somehow summarized in terms of wheels.
Uh-huh.
So basically cyclic graphs rather than trees. And I don't know, it looks so similar that I just had to ask the question. That's all.
of course, Préli is a very small operad, and this can be done with any operad. So maybe the gros operad of, or some bigger operads would be more closely related to these wheel things.
Okay.
I don't know.
Sorry for taking from your time.
Oh,
We have the time.
thank you.
Any other questions? So let's thank Frederick again. Let me remind you that we are going to Bill's restaurant. Do not record that. So let's meet. I propose that we meet at 6 in the lobby. For those of you who don't know where this is.